Hello to everyone. Thanks for watch my videos, and today we will talk about the tail. So the tail is made by two wings, the vertical and the horizontal. They have three main functions. The most important one, the first is the trim, the second is stability, ensure stability, and third is control. Okay, trim means balance, and the more if the aircraft is badly trimmed, you will need to fix with your stick, and you will reduce the flight time of your battery, because the servo will be on every time moving. So if the aircraft is well trimmed, you will have a very long flight time. Okay, just go ahead and first of all, there are several types of tail, and we can see here we have conventional, double, canard, three canard without vertical fin, vertical wing. We have conventional with canard, and also we have delta wing. Every type is suited for one type or another. Every depends on the engine and of the airplane configuration. So this is, as you can imagine, this is a trial and error procedure. So we have the conventional wing, the conventional tail. We have the T-tail, we have the cross tail, we have the V-tail, the Y-tail, double tail, tandem, and this is I don't know how it's called, but every type of tail is suited for a is characteristic for a type of engine. For example, we will see that the most common is T and cross. This one is for jet fighters, which have the engine here. So everyone is characteristic. So just one thing is, when you are deciding the plane form of the wing, just keep in mind that we have 5 types of sweep angle. Zero sweep angle, plane. Sweep angle on the leading edge, sweep angle on the half chord, sweep angle on quarter chord, and sweep angle on the trailing edge. Every type is better for one type of aircraft, and performance better than another. Okay, here, let's see, maybe it's better here. Okay, this is one of the thing I'm talking about, referring to. Depends on the type of tail, we can have problems or avoid the problem of the spin recovery. What is spin recovery? Spin recovery is when the aircraft is the incidence, the angle of attack is too high, so the aircraft goes in stall and then start to spinning. You can check their videos on YouTube. If you type spin recovery, you will see a lot of video of this. The only surface in the aircraft that can recover the system from spin is the tail, not the horizontal but the tail. So in this case we have the horizontal is blanketed for the wing wake. So if we put here or here, we will have some control, not during the spin recovery, but some control during climbing, for example, because this is stalled. But for spin recovery, remember that the wing, the rudder is the only surface that can recover the aircraft for the spin. But this picture helps you to set up the horizontal stabilizer. We will see later how to set up the vertical the horizontal stabilizer in order to allow the vertical wing to recover the aircraft from spin. It sounds a little bit difficult, but you will see later. Okay, so I'm going fast, not because I'm fast now, but because I saw that many of you watch about 4 minutes of a video, so I'm trying to just make a big wave of thoughts, of technical advice, and then you can see this video a lot of time. It's not a lesson once time. You can repeat the video a lot. So here we see what I told you before. Depending on the location of the horizontal stabilizer, we can have the spin recovery, the recovery of the aircraft during spin. If the tail is inside the wake region, we will have some spin recovery, but will take a lot of time to recover the aircraft, but is not impossible, but can be better. For doing this, we have to draw a line with 60 degrees on the leading edge and 30 degrees on the trailing edge of the horizontal stabilizer, and then we can see if the tail falls inside the wake partially, totally, or doesn't fall. In this case, we will have very little control from the rudder to stabilize the aircraft from the spin control. In this case, we have this surface that can help us, and in this case we will have all. So very nice. Also, we have to take into account that the diameter of the propeller and the geometry of the horizontal stabilizer, because if the horizontal stabilizer is completely inside the propeller wake region, we will have some problem with stability. The aircraft we will fly, but the stability and the trim is not so very nice. Okay, so another main function of the aircraft of the vertical tail is to counterbalance the force created by the propeller when rotating in a propeller engine. We can see here we have the propeller that is rotating in one direction, and the vertical wing creates a lift in order to balance the yaw moment and avoid the twisting of the aircraft. Okay, so this means that the profile of the vertical tail is not symmetrical but have some camber, and the camber is located in order to create some force to counterbalance the torque moment. In a jet reaction engine, in case of failure of one engine, we have to use the trim of the aircraft, of the rudder, to create a force in order to avoid that this TR, the thrust of the right, tends to rotate the aircraft. So this force should counterbalance all this the thrust of this engine. I will show you just some details to understand what I'm thinking, what I'm talking. So sorry. Okay, so first of all, we have this is the P51 Mustang, and as we can see here, we see that the tail is not symmetrical, but we have some camber and some offset angle. You can check also on pictures of it on internet. Everything is there. You have to just to search for. We have a Messerschmitt, and also we have that the root is not symmetrical, but we have some camber. And then lastly, we have the P40 Kitty Hawk, and then I will show you here which the same configuration. You see there is a camber, and this is not symmetrical. So just keep in mind that when you are locating the vertical wing, you have to create a lift in order to counterbalance the yaw moment, because as you can see, all these aircraft have the number of engine is even 1, 3, 5. With the pair number 2, 4, 6 is not necessary, because they are the engines are rotating in opposite direction, the right and the left engine, so the yaw moment is balanced. Okay, so what we need to draw a tail, a vertical tail, a horizontal stabilizer, or call it as you want. The name is okay. We need to know just a few things. One of these is that all the tail is characterized by one coefficient, which is this one, volume coefficient. H stands for horizontal and V stands for vertical. We have these four numbers, which means that L is, we can see here, we have L, which is the distance from the aerodynamic center of the wing to fuselage to the aerodynamic center of the horizontal. Okay, then we have SH, which is the surface of the horizontal stabilizer. We have C, which is the Mach, mean aerodynamic chord. So this means that you have to know the geometry and all the parameters of your wing. And lastly, we have S, which is the surface of all the wing, not the apparent surface, but the overall, which means that all the surface of the wing. Okay, you can calculate this volume, but this is a trial and error, so this can take a lot of time to calculate. The best way to go ahead is just to take this table and start with some values of the horizontal and vertical volume. These are more generic, okay? If you want to build, let's say, a fighter, we have this volume. So this means how to use it. Okay, this is very simple. This is very simple. If you have this coefficient known, you can calculate one of this one, because one of these should be unknown. Or the surface of the wing of the mean aerodynamic chord, or the distance between the aerodynamic center to the wing fuselage towards the aerodynamic center of the horizontal stabilizer. So taking the two values, you can start to build something. Then how to calculate the surface of the horizontal or the vertical wing? Just study some geometry and you can calculate, because there are several forms, but all of them are there is some geometrical figures. I will show you just one. We can see here, we can calculate the root. We have all these parameters should be known. So this is what I mean when I say by trial and error. It means that you have to know something. I will show you, for example, with this type of wing of tail, the propeller is in pusher configuration, not tractor. The tail, T tail, and also just take a look on the how it's built. We can see here that for the Pilatus we don't have nothing. We don't have tapering. We have the same profile from root to tip, without no sweep angle, no taper angle, no twisting, nothing. We can see here what I'm telling you. Yeah, no, sorry. What is it? Okay, yeah. Okay. As we can see, for example, taking as an example the Pilatus, you see this part? Okay. This is what I say. Okay. This is the vertical rudder is outside the wake. We can see also here we see that the vertical wing is little bit aft the horizontal stabilizer. So this is for spin recovery. In this case, we do not have the problem, because the T-tail is better, because we have the wake region during stall. The vertical wing is outside the wake, so is another advantage. Also here, as just take a look how it's built. This part, the ventral fin, is an enhancement of the function of the tail. Is just an extension. Also for jet engines, the best configuration is the T-tail, because the rudder, the horizontal stabilizer is completely outside the wake of the fans of the turbines. So every time we will have control, trim, stability, and also spin recovery, just in case. Just take a look that the stiffness of the aircraft increase with the increase of the power, speed, and so on. So just take a look in order to see how you can draw a vertical tail. Okay, so I just want to show you here we can have some details. In this case, for example, if we draw our lines, we can see that the upper part of the rudder is not blanket, so we have some control during spin. Okay, just go to the drawing. This is how should look like. And okay, so there are, as you can see here, there are 3 assemblies. Sorry. Oh yeah, 3. We have this one, and this one. Okay, just to go to the vertical wing, I did not make some rudder because I show you in previous chapter how to build an aileron from the wing, so it's the same, the procedure is the same. Okay, this is done by using this information I took from this book, which there are several data. Okay, yeah. We can see that, for example, for Cessna, we have root 0012 and tip 009. So I downloaded the coordinates of the airfoil and then start to build just one by one. In the end, you will have something like this with 10 vertical stations, and also we will I prepare an Excel spreadsheet. Sorry, I prepare an Excel spreadsheet because it is better to understand. We have the coordinates downloaded from internet. We have station 1 with 200 millimeters, and at the mid station I will change for the 009 airfoil. This is a arbitrary decision, it's not written in no parts. You can decide to make only the last section, I mean the tip airfoil section with the 009, or just start from whatever you want. I decide to make half vertical tail with a 0012 airfoil and the other half is with 0009 airfoil. Is my choice, is up to me. So I prepare all this spreadsheet, and as you can see there is a formula inside. We have a taper ratio of 0.5, so this means that if the root is 200, the last root is 100. And then we have some calculation, some values, some coordinates, and in the end we will have the vertical tail. So just we wait a little bit. Okay, Yeah, there are too many things open. Okay, so I build the distance between every section is 10 centimeters. The thickness is 3, and I made if you want to make some the diagonal cut this one. Okay, I will show you how to do it. I did this cut sweep, okay, and this is done by a 2D sketch and 3D sketch. The 3D sketch is for direction. The 2D sketch is what I am cutting. Okay, so I made this, then this, the guidelines, and then cut sweep. I will show you how this looks like. You see? Okay, just one important thing, very important. When you are making this type of cut, you need to start to cut from the wing tip and not from the root. Just remember these words: cut from the tip, not from the root. This means that this drawing is here, this drawing is here. Okay, every drawing is on the tip, not on the root. I did not draw from here and extrude from this part. The reason is very simple, because when you are drawing this, you can adjust the length of your extruding. Okay, you can cut from here. If you do in the opposite direction, it's not good. Just keep this, use this. Also, when you are positioning the spars, this rod, sorry. Okay, first rule, make the geometry with the right angles in order to avoid rotating of the section like this. If you choose a cylindrical rod, the wing can rotate on one axis. If you use vertical right angles, cannot rotate. Then when you are mating, okay, when you are mating the spar, start to mate from the tip, not from the root, because if you mate from the tip, you can adjust the length of the extruding part. But if you mate from this part, you will not, you can adjust, but the result is not the same. The result is not the same. Just start from here, is better, but you can try whatever you want. I mean, I'm not the master of aeronautics. Okay, so once you have this every hole you see here is by myself. There is no rule. I made just, I will show you just to know. No, I did one which is 9 degrees, and then the other one is random angle. The story is that near the root we need to have very stiff integrity, with very stiff structure, sorry, and in the end we need to have just a little bit, not because the tip is strong, but just for weight. This is the famous cantilever configuration. Okay, so once you have the wing, we have the overall assembly. Okay, so I did this part, which is the transition, the connecting part between vertical tail and fuselage. How I did it, this is again, this is my choice. I did not see in any book. Okay, I made this part, which I extrude the same airfoil of the root. Okay, this is the cut, you can see. Then I did some slots here. I will show you one. Okay, this is one slot. You can imagine from this. And we have all these ribs from of the fuselage which are done in this way in order to very lock the structure, you know. So we have that if you glue all this part, all this system will be a unique part, cannot rotate, cannot be nothing, it's very stiff. So then, as in the end of all, you will cover all with this, but okay, it's very okay. So I think that this is all you need to know about how to build a vertical wing. Okay, you can see this protruding part, but it's for laziness, not for if you want to remove, you can shorten your extruding, or you can make a cut and cut everything. It's up to you. But when you will build this, of course you will not have these problems. Okay, so thank you very much again to watch, and bye bye. Oh, sorry, no. So for a recap, all the things we saw, if you want to draw a vertical wing, you need to know, you have to make a choice, and the first choice is the volume coefficient. Once you have the volume coefficient, you can start to calculate all the parts. So you can draw all your wings, all your fuselage, everything, and then with that value, boom, use the coefficient and locate the vertical and horizontal wing of the tail accordingly. Okay, just keep in mind that the fuselage plays a role also in the tail configuration, but not so much important. Okay, as usually, I will show you the box I used, so you can study by yourself. Okay, the first one is Aircraft Design, a very nice book. Then we have the General Aviation from Mr. Snorri Gudmundsson. Okay, that we have here a very useful information, and also the methods and calculation. Very deep, very well explained, but I did not tell you nothing of this because otherwise this will take a lot of time. Then we have this fabulous book, Scale Aircraft Wing, which recalls very drawing of Mr. Wylam. And last one, Roscam. This is the one of the Bible of aircraft design. Roscam Airplane Design Volume 1 to 7. So thank everyone to see this video, and bye bye.